Okay. Hi, everyone. I'm Marta Brioschi, and I am a PhD student at the University of Milan. And today I will talk about all-optical generation and time-resolved polarimetry of magnetoacoustic resonances via transient grating spectroscopy. But first, I would like to introduce the framework of this topic, which is acoustic control of magnetism for spintronics. And this is a very active research field because of its technological potential, as you could also seen from the previous presentations. And the technological potential relies on the fact that you can speed up the writing process, for example, by acting on the magnetization state of free layer in the magnetic bits. So the idea is to find the waves that are at the lowest energy cost and that require the least amount of time possible. And in particular, you can exploit acoustic waves to act on the magnetization state and dynamics via magnetoelastic coupling. And this is a pretty efficient approach, as has been shown, for instance, in this study, where phonon-driven magnons have much higher amplitude and lower damping with respect to magnons generated by thermal pulses. And in addition to that, it has been proved that also the radio frequency field generated by acoustic waves can be used to induce precessional dynamics that can be exploited to achieve magnetization switching and to drive ferromagnetic resonance, which is the main topic of this talk. So what is ferromagnetic resonance? If you have a magnetic moment in a static external field, the motion is described by the Landau-Lipschitz-Gilbert equation, and it's given by the composition of the Larmor precession and the Gilbert damping that will eventually make the magnetic moment align with the static external field. However, if you have a radio frequency field that rotates at the Larmor frequency, you can reach ferromagnetic resonance because the radio frequency field can act on the magnetic moment and balance the Gilbert damping, making the magnetic moment precess at a constant angle with respect to the static magnetic field. And the interesting fact is that the radio frequency field can be an electromagnetic wave, as it happens in standard fMR measurements in cavities, but can also be the radio frequency acoustic field generated by acoustic waves, for example. However, in order to reach acoustically driven ferromagnetic resonance, you need the spin wave dispersion and the acoustic wave dispersion to be at some point degenerate. And this can happen in the gigahertz frequency range and in the inverse micron wave vector range. In particular, if you fix the wave vector, you can make these two dispersion degenerate by tuning the external magnetic field. So in our case, we adopted an all-optical approach to generate surface acoustic waves, which is based on the transient grating technique. In the transient grating technique, you have two coherent pump pulses that interfere on the sample to generate a transient intensity grating, which allows you to generate surface acoustic waves via thermal expansion at fixed wave vector. And the wave vector can be tuned by acting on the geometry, namely the angle between the two pump pulses and the pump wavelength. So the transient grating acoustic dynamics can be then probed by a third laser beam that gets diffracted by the transient grating, because the transient grating also induces a periodic modulation of the optical constants of your sample. So if you look at the intensity of the diffracted beam as a function of the time delay between pump and probe, you can have an idea of the active acoustic modes in your material. In our case, we studied a nickel thin film on a calcium fluoride substrate, and we observed that we are able to excite two surface acoustic waves of the substrate, which are the Rayleigh surface acoustic wave and the surface skimming longitudinal wave. I would like also to point out that since nickel is a highly magnetostrictive material, these two surface acoustic waves also generate spin waves of equal wavelength by inverse magnetostriction. So since we are interested in how the surface acoustic waves affect the magnetization dynamics as a function of an in-plane magnetic field, we also implemented the time-resolved Faraday polarimetry. So we used the transient grating pumping mechanism to generate the surface acoustic waves, and we used a third beam for the Faraday polarimetry, which means that basically we looked at how the polarization of the transmitted beam changing as a function of the time delay between pump and probe. So this is what we obtained. And here you can see the intensity of the Faraday signal as a function of the time delay and the external magnetic field. And as you can see, both periodicity and amplitude strongly depends on the external field. And if you look at the Fourier transform of this 2D map, you see clear resonances that happens when the magnetic field is such that you have degeneracy with the acoustic dispersion, which is in line with the fact that the resonances are exactly at the frequency of the transient grating induced surface acoustic waves. So, and if you change the geometry of your experiment, so if you tune the angle between the two pump pulses, you're able to change the frequency of your acoustic waves. And so you can basically shift these resonances in both frequency and magnetic field. And this is quite useful if you want to compare your acoustically driven FMR results with standard FMR experiments. And to do so, you also need to extract some useful information from this kind of map, such as the peak position, which gives you the frequency and magnetic field at resonance, and the magnetic field line width of this peak, which is useful to extract information about the damping of the magnetization dynamics. So we did perform a standard FMR measurement on the very same sample. And here you can see the comparison between the two techniques. And we also used the formalism and theory behind standard FMR to extract some relevant magnetic parameters of our sample, such as the effective magnetization, the Gilbert damping, and the inhomogeneous broadening term, which gives you information about the magnetostructural disorder of your sample. So here you can see the frequency at resonance as a function of the magnetic field at resonance. And by fitting the two data sets with the Kittel formula, we were able to extract the effective magnetization. While here you see the magnetic field line width of the peak as a function of the frequency at resonances, and you get some linear dispersion. And from the fit, you can extract the Gilbert damping and the inhomogeneous broadening term, respectively, from the slope of your fit and the intercept. So here you can see the numerical values that we were able to extract, and they are like fully consistent within the two techniques. So to conclude, we were able to probe simultaneously the acoustic and magnetic dynamics by combining the transient grating spectroscopy and time-resolved Faraday polarimetry. With the transient grating spectroscopy, we generated surface acoustic waves that also excite spin waves at fixed wave vector. And by tuning the in-plane external field, we observed acoustically driven FMR. And then we also compared our results with the standard FMR, and we obtained fully consistent results. So yeah, to conclude, I would like to thank all the people that contributed to this work. And I would like to remind you that the Transient Grating setup is now open for users. So if you're interested, you can go to the Trieste and FFA website and submit your proposal. Thank you for your attention.
Thank you very much, Marta. Yeah, it's time for questions, audience. So now you have the chance to ask questions live on Zoom and then later in GatherTown. So can you maybe go to slide 11 then?
Yeah.
Because now we can see the slide numbers. That's handy. So in this contour map down on the bottom right side, well, what happens when you go to higher magnetic fields? I'm a bit confused by that whole thing. So are these? What are the modes we're looking? Yeah.
Basically, if you go to higher magnetic fields, you see nothing because you lose the degeneracy. I mean, you will see resonances at higher magnetic fields if you can generate acoustic waves at higher frequency, because there you will have the matching of the spin wave and the acoustic wave dispersion. But in this case, you will actually see nothing. So.
Okay, yeah, now I got it. Can you maybe remind us what the two abbreviations are? Because yeah, you mentioned the names, but
yeah, this is
I like to have pictures.
Yeah, sure.
You can see how things move.
This is the skimming, surface skimming longitudinal wave, which is the faster one that we observed. This one, and then it's the Rayleigh surface acoustic wave, the slower one.
Okay. Oh, Claire, yes. Oops. No, I think we are simultaneously muting and unmuting you over and over. Okay.
Perfect. Thank you very much for the nice talk. I was wondering, maybe this is a stupid question, but is there any way to get some spatial resolution here?
In which sense? If you
then you're kind of doing a global measurement, right, of your
yes.
Your samples. So is there any way to do this with like a focused?
Yeah, this is actually. I mean, I think that the scheme is misleading because the sample is actually much larger than the laser spot, because the laser spot is about 50 microns. And yeah, so you're actually doing a local measurement in this case.
I see. But would you be able to focus your, let's say, beam time below that, you know, and do some sort of scanning across your sample?
This setup would require a lot of work, but yes, in principle, yeah. Okay. The important thing is that you have enough stripes of your transient grating to launch acoustic waves. Okay. That's the only requirement.
I see. Thank you.
Welcome.
And there's a final short but very general question by Anna. Anna, do you want to ask it yourself? Anna? I think you can now unmute yourself.
Yes, I think I can. Sorry. Thank you for sharing. I was really impressed by this work, and my question is, what other materials can be as your researchers' goal?
Sorry, I didn't quite get it.
Here you use silicon with something with 9 nickel, as I saw. Can it be some other materials?
Yeah, of course, as long as it's magnetostrictive, of course. And yeah, in principle, you can do it with any materials, also because you don't have to go in transmission. You can also implement the exact same results also in reflection, which it makes the class of materials you can study much wider.
Okay, thank you.
I don't know if I answered, but okay.
Yes, you answered.
Okay.
Thank you.
And you can also continue the discussion in Gathertown in the bar.
Okay, yeah, sure.
Okay. And then thank you again, Marta, also for
Right.
answering the questions.